Hi, everybody. I hope you had a good Thanksgiving. It is Sunday night right now. I just got back from a trip up to Illinois. That was fun. And I went home. It's about 10, yeah, about 10 p.m. And we are ready to do our last calculus lecture of the semester. And actually, our very last video of the semester. So yeah, this week should be a pretty chill week in terms of calculus. Um, we're just gonna look into some new interesting applications of integration today. We're gonna look at moments and centers of mass and hyperbolic trig functions. And then the rest of this week, we're gonna be reviewing for our final exam. And I guess, catching up on anything that is not done. So yeah, I like to leave the week before finals fairly reserved so that, you guys have time to catch up on stuff and not be exhausted during finals week. Cool. So moments, centers of mass, and then I'm gonna throw you a video for hyperbolic trig functions. But yeah, moments, centers of mass, especially for the engineering folks, is a relevant thing and will be something that continues to pop up, especially in Calculus 3 later on. So we're going to get introduced to this today and elaborate on it in about a year. Okay, so what is a moment? A moment is a torque about, it's a force where you're pushing down and, creating some kind of torque on a lever arm on a rod. And this moment is calculated, all right, let's call it M for moment. And actually, I'm going to put a subscript of Y there. Yeah, okay, let's make this all green, that's fine. Moment. The subscript of Y there is because this is going to be the moment about the Y-axis, and the Y-axis is vertical and would be given to us by the equation x equals 0. And so, yeah, we're going to be figuring out things relative to x equals 0. We're going to be dealing with x values here, but we get a subscript of y here because it's y-axis. This moment is equal to the product of a mass and a distance I don't know, we could label the mass m and the distance maybe something like, I don't know, xi for the ith point mass that we're using. I guess we could label it, for each mass that you might have, you could give it an index, and for each distance that you have. But yeah, the distances will be x values. So let's actually label this seesaw that I have with some masses and some distances, and then we'll actually calculate some moments. So left side's the heavier side. So let's say we've got 10 kilograms over here, 8 kilograms over here. And then I know that this is not drawn particularly this way, but let's say that we've got 5 meters over on this side of the seesaw and 4 meters on the right-hand side of the seesaw. And yeah, I'm going with metric units here. If you want, American units, you can go with eagles per American pie, or per apple pie or something like that. But yeah, the moments that we'd be calculating would be kilogram meters here, because we're going to be multiplying. So let's take a look and find the center of mass of this entire object by using some moments. So this is the center of mass in the x direction. That's going to be given to us by finding the sum of the moments. I have this down here. It's the moment of the system about the origin over the mass of the system. So I don't know, we're gonna add up a bunch of moments on the top, and then we're gonna add up mass on the bottom. And so for this, particular seesaw, we would have a couple of moments. The first one would be 10 kilograms times, we'll call that -5 meters here because that's to the left of x equals 0, plus 8 kilograms times 4 meters. And on the bottom, we'd sum up the masses, which would be 10 plus 8. What this represents in my mind is a lot like a weighted average. What we're doing is, we're measuring these moments, the torques on the seesaw, by multiplying the mass times the distance away, and the masses get weighted by that distance away. And so, finishing this out, we've got -50 plus 32 over 18, -18 over 18, which is -1. So what does this mean? What this means is that if we shifted over the fulcrum over 1 meter to the left, then both sides would be balanced. If I do a real quick drawing of what this would look like balanced, 4 meters on this side and 5 meters on this side, and then 10 kilograms on this side and 8 kilograms on this side, then each of those moments would multiply and equal 80. This in the negative direction and this in the positive direction, so that the seesaw would be completely balanced. So that's kind of the idea here. We've, in this example, we've got two masses, which really we're treating as like point masses that are, a given distance away from the origin here in the middle. But what would happen if, instead of something discrete like this, where we've got one mass on the left and one mass on the right, and we haven't even considered what the mass of the seesaw is, all this other stuff is, completely massless in the treatment that I just gave it. What if we look at something a little bit more interesting and say, instead of having a uniform seesaw, what if, I don't know, we had a seesaw that was shaped like a cone? And in order to balance that cone, we'd probably need to, move over to the right-hand side. Or, like in this scenario, we've got an object with less volume on the left-hand side and more volume on the right-hand side. It could just as easily be something that has density that changes throughout the material. In this kind of a scenario, we wouldn't be able to just, take the sum of 2 point masses and, find their weighted average to get the center of mass. In this case, we would be summing up a whole bunch of point masses if we, went along and at each part, maybe we looked at cross sections in our lever arm there. And yeah, if we were adding up a bunch of cross sections, that would be, an approximation until we kept, making the number of cross sections larger and larger, using the limiting process to make this, instead of just being something discrete, into an entire continuous integral. And yeah, like we've seen how to take volume by cross sections, and that's kind of exactly the idea of what we would be doing here. Finding the volumes of this object by cross sections. And the idea is this thing where we've got a sum from I equals 1 to n. We take the limit as n goes to infinity, and we get integrals. And so, here are the integral definitions of finding a moment about the origin, the mass of an object for a given density function. The density function is given by this variable that looks like a p, but it's actually the Greek letter rho. And I'll just write that. I think technically RHO would be the way to, abbreviate that letter. But yeah, that's the Greek letter rho, and it's commonly used for density. And so in order to find the mass of an object, you are, at every point along that object, your density function is giving you a value. And if you add up the densities throughout the entire object, you get the mass of the object. And then the moment integral is just like the mass integral, except instead of, just integrating over the density function, we are multiplying the distance times the density function that's getting accumulated over the object, which gives us the mass times distance moment that we were looking for. And then the center of mass, just like we had up here, it is the moment of the system about the origin, and that's divided by the mass of the system for scaling. It's their weighted average. Yeah, these two integrals will be important, and we, take the quotient of those two integrals to find the center of mass. Yeah. All right, so example number 1. We are supposed to compare the centers of mass of 2 1-meter long steel rods, the first rod with a constant thickness and a density of 0.5 kilogram per meter, and the second one thickening from left to right so that its density is x units from the left end is this quadratic function. So the idea here is, yeah, from left to right, this thing keeps on getting more and more dense. I made a little GeoGebra. Let's see if I can pull that up. Oh, see, it's right there. Got it pulled up twice. It's fine. Bye. Okay. So first one is we have our rod of constant thickness, and that thickness is 0.5. I actually just learned in GeoGebra that there is a revolve around like a surface of revolution here. Let's see, surface of revolution. Super cool. You just click on the curve and then you rotate it around the axis and it comes up with the parametric surface for you. First time I ever knew that. So there's our rod of constant thickness. And the other one, now this is a little bit weird. This is like the visual representation of what the density would look like. Physically, you could have a rod that looks like this, but the underlying material changes so that its density function looks like this, so that it's lighter at the left-hand side and heavier at the right-hand side. And yeah, this is something that doesn't necessarily even have to be density for mass. You know, you could have a rod that has varying temperatures, and if you wanted to take the sum of the temperatures along the entire rod, you know, you could have a temperature function instead of a density function. Yeah, and we'll do that kind of stuff in Calc 3. But here's the idea. In order to find the center of mass, come on, of the first one, we're taking the ratio of two integrals. We've got our moment integral on top and our mass integral on the bottom. And for the one that has a constant density, and the density's 0.5 kilogram per meter, that constant just can come out in front of the integral, and the integral works out pretty simply. You end up getting 1/2, like you might expect. If something is of uniform thickness or uniform density, then yeah, it makes sense that the center of mass is directly halfway through the object. And yeah, even though it's 10:26, I thought it was a good idea for me to actually, work one of these out. And apparently working out the hard one was the good idea. So the idea here is we will be doing the same thing, except this time using this as our density function. So for the top one, our moment integral, we would be going from 0 to 1. It would be x times our function. Our function is 0.5 times the polynomial 1 plus x plus 1/3 x squared dx over, oh, that doesn't look like, looked like a 4. Over the mass integral, which would just be the density function part. So 0.5 times 1 plus x plus 1/3 x squared dx. And the idea here is we take antiderivatives. I'm going to bring the 0.5 out front on both of these. And then I'm going to multiply x into the top one so that we're taking the antiderivative of x for the first term, which is 1/2 x squared. And then for the next one, we would have x squared, which would be 1/3 x cubed. And then for the next term, that would originally start out as 1/3 x to the third, but when we take the antiderivative, we get 1/12, yikes, x to the fourth. And that'll be evaluated at 0 and 1. And the bottom one should be simpler. This one we would just have x plus 1/2 x squared plus 1/9 x cubed. 1 and 0. So yeah, the zeros in both of these scenarios are just going to be completely 0. So we're going to have 1/2 plus 1/3 plus 1/12 over 1 plus 1/2 plus 1/9. And there was some part of me that thought, doing this fraction arithmetic would be a good idea. All right, we're going to finish this and we're going to get something. I mean, if we're looking at that picture that I had on GeoGebra, we are, possibly expecting that since we get wider over on the right-hand side, then it looks like, significantly wider, that maybe our center of mass has shifted. Instead of being directly in half, maybe we're a little bit over a half. So hopefully we're going to get a fraction that's a little bit more than a half here. All right, on the top, that is 6/12 plus 4/12 plus 1/12, which is 11/12. And on the bottom, we have 18/18 plus 9/18, that's 27. And then 2/18, which is 29/18. Ooh, all right. And so in order to do this, we've got 11/12 times 18 over 29. The 12 and the 18 cancel out pretty nicely. And I think that's all that happens, so that we get 33 over 58. Boom. Okay, so 33/58 would be the center of mass of that second one. Cool. The next topic number 2, I am going to skirt over this pretty quickly. It's mentioned here in the book, and there are several examples about this, but it will be more natural to speak of this kind of thing when we learn double integrals in multivariable calculus. The idea here is, when you are orienting a two-dimensional teeter-totter, where you've got differences in x values and you got differences in y values, and you can teeter-totter in any direction you want. We're going to need to calculate two centers of mass, one in the x direction and one in the y direction, in order to get the exact center point. And this C is not necessarily just for C because of center. There's actually a special word for kind of the center of mass of an object, especially a two-dimensional object like this. It's called the centroid. Yeah, and the centroid is kind of, yeah, it's the center of mass of the object, as long as that object has constant density. Yeah, whenever, in calculus 1, whenever we're working with a two-dimensional object like this, we're not going to have the freedom to have a variable density like we were when we were just working with a one-dimensional object like a teeter-totter, where there was only one direction that we were calculating the center of mass in. Here we could have variable density, you know, like in the case of these two rods. In this case, we can step it up a dimension in terms of the underlying space that we're looking at, two-dimensional shape rather than just a one-dimensional left or right. But yeah, we can't have a variable density. We're going to have to make it a constant density in order to be able to just do this in single variable calculus. When we get to double integrals, we will be able to step it up and do variable density again. When we get to triple integrals, we're going to be able to have solids of variable density. It's going to be great. When we get to line integrals, we're going to be able to go through space curves of, you know, variable density. There's some stuff to look forward to there, but we're not going to get into maybe the nitty-gritty details right now. Yeah, in order to do this, you would calculate a moment about the x-axis and the y-axis. Notice that those letters change because the x-axis is y equals 0, and the y-axis is x equals 0. And so, yeah, you're calculating moments based off of those axes. Right. And, you know, notice here that the differentials are not things that we've necessarily talked about yet so far. We've got a dA here, which is an area differential. Yeah, which we will get into more details in multivariable calculus. You could do this right now, but you just need to be careful with the, you know, how you're setting things up. So yeah, in this chapter, there is an example number 2. I'm not going to do it. The idea for this, did I actually? I copied it for the Theorem of Pappas. Anyways, you know, in order to do a problem like this, you would need to calculate the center of mass in the x direction and then the center of mass in the y direction. And as you're going along, the density that you would be finding is basically the top function minus the bottom function to calculate the amount of material that you have at each part. You're calculating, yeah, kind of the height of each cross section there. So yeah, you could totally do that, you know, find the center of mass of a shape like that. You could find the center of mass of a shape like this. You know, notice this one has a center of mass at 6/7, 3/8, because, you know, things are shifted over that way. Cool. Yeah, and if you get into doing stuff with arc length, you can even, you know, calculate the center of mass of something like a curved wire, where, you know, all of this volume's not, or all of this area is not fitted in. Yeah, you could do that, you know, with single variable calculus, which is cool. Those things will become more generalized and honestly a little bit more conceptually easier to understand when we learn about double integrals, triple integrals, and line integrals. One of the cool things at the end of this chapter, though, are the theorems of Pappas. And what this is an easy way to calculate the volume of solids of revolution. We've already looked at, the shell method and the disk washer method for calculating volumes of revolution. But what Pappas understood, he's an ancient Greek, is that the volume of a solid formed by revolving some region around a line of an axis of rotation, that's what L is, would be the area of a cross section, as and that cross section has to stay consistent the entire time. We're just revolving this around the axis of rotation. So as long as you've got a constant cross section, it's the area of the cross section times 2 pi times d, where d is the distance. Okay, let me get here. From the axis of rotation to the centroid. So yeah, as this thing spins in a circle, the centroid would travel a distance of 2 times pi times d. That's where we get this, and then we're multiplying it by the area of the region. And if you want to look at a proof of why this theorem works for volumes, it's based on the shell method. You could, consider adding up a bunch of, shells of this kind of thing. And yeah, here we've got the centroid, the x coordinate of the centroid playing an important role there. Cool. So using Pappas' theorem, we could more easily find the volume of this torus, where we are just rotating a circle around some axis of rotation. All you'd need to do is calculate the area of the cross-section, pi r squared, little r, and then multiply that times 2 times pi times the big radius to the centroid of that cross-section. And yeah, you get a really nice volume formula for that. And it would have taken quite a bit more steps if we were going to do that with the washer or shell method, a couple sections ago. Similarly, there is a Pappas' theorem for surface areas, which, deals with rotating arc lengths around an axis of rotation. And again, that is the distance that the centroid covers. So 2 times pi times t times the length of the curve that you're using to make the surface. And yeah, you'd use an arc length integral for that one. And yeah, those are the important parts of section 6.4. Moments and centers of mass in general, and calculus, because we want to deal with variable densities. We use the limiting process and look at integrals to calculate moments and masses. That's what that looks like. And yeah, we will be able to find centers of mass of more interesting shapes, and we're going to do that in more depth in Calc 3. For the other kind of, fun thing here, I have a video linked for hyperbolic functions. Yeah, because section 6.6 in our book is about hyperbolic trig functions. And our book takes, a more clinical approach to the hyperbolic trig functions. It gets right down to business in terms of focusing in on what are the definitions, derivatives, and integrals of hyperbolic trig functions, and then what are the inverse hyperbolic trig functions. So cool. But I'd like you to watch this video. If you've never seen a video by Zach Starr before, generally they are of high quality, and this focuses more on the applications of hyperbolic trig functions, so that, if you ever come into an application like this, you'd know where to look in our book. It's in chapter 6.6. But anyways, this might be a little bit of a quick day. And if you guys end early, that is not the end of the world. I'll see you guys tomorrow, and we will review stuff that was on the first test, like limits and that kind of stuff. Okay, so I'll see you tomorrow. Bye. But you guys watch the video, okay? And then leave. Okay, see ya.